Hello there, and welcome back to Nick's Documentaries, where we venture into the deep silence of geological time and listen to what the Earth itself has to say. Tonight, we're embarking on perhaps our most ambitious journey yet. We're going to watch the world break apart and come together again. We're going to see oceans born and oceans die. We're going to witness continents drift like slow ships across the surface of a planet that has never, not for a single moment, been still. This is the story of Pangaea, the last great supercontinent, and what happened after it shattered. This is the story of how the map, the 7 continents, the 5 oceans, the familiar shapes of Africa and South America and all the rest, how all of that came to be. But more than that, this is a story about time itself, about changes so slow that no single lifetime could witness them, yet so vast that they've rewritten the face of the Earth completely, again and again, in cycles that stretch back billions of years. Now, before we begin this drift through deep time, I'd love to know where in the world you're listening from tonight. It's a question with more meaning than you might think, because the ground beneath your feet, wherever you are, has traveled. It's been to the equator and the poles. It's been underwater and thrust up into mountain ranges. It's been part of different continents, under different skies. The place you call home has moved thousands of kilometers from where it was when dinosaurs walked, and it will move thousands more before the Earth is done with it. And if this kind of planetary scale thinking draws you in, if you find yourself wondering what the world looked like before there were humans to see it, I'd be grateful if you tapped like or subscribed. It helps this quiet exploration find others who look at maps and see not just borders and countries, but the restless surface of a planet still in motion. So settle in, let the stillness around you deepen, and prepare to watch in your mind's eye as the world transforms. Mountains will rise and crumble. Seas will flood continents and then withdraw. Land masses will collide with the force of slow-motion catastrophes, welding together only to tear apart again millions of years later. And through it all, life will adapt, spread, diversify, creating ecosystems that exist for a time and then vanish when the ground beneath them moves. We're going to start some sensor million years ago, in the late Carboniferous period, when the continents were still drifting toward each other, gathering like guests at a cosmic reunion. We'll watch them meet, forming Pangaea, the All-Earth, a supercontinent so vast that its interior was a desert larger than any that exists today. Then we'll watch it break apart slowly across back million years, spawning the Atlantic and Indian Oceans, isolating Australia and Antarctica, shaping the world we know. But we won't stop there. We'll look forward as well, because the Earth isn't finished. The continents are still moving. The oceans are still changing. And if we wait long enough, if we could somehow watch for another million years, we'd see the world transform again into something that would be as alien to us as our current world would be to someone from the age of Pangaea. The maps are moving, the oceans are breathing, and the planet beneath us has never known stillness. Let's begin. To understand Pangaea, you first have to let go of the idea that the Earth is solid and still. It feels that way, of course. The ground beneath your feet seems permanent, unchanging, the very definition of stability. We use solid ground as a metaphor for certainty, for things you can depend on. But it's an illusion, a trick of the timescale we experience as humans. The Earth's crust, the thin rocky skin we live on, is broken into pieces called tectonic plates. These plates float, in a sense, on the hotter, more plastic layer of the mantle beneath. And they move, not quickly, typically a few centimeters per year, about the rate your fingernails grow. But they never stop moving, and over millions of years, those centimeters add up to thousands of kilometers. This movement isn't random. The plates are driven by convection currents in the mantle, by heat rising from the Earth's core, by the planet's own internal engine of radioactive decay, and primordial heat left over from the Earth's formation, Wu billion years ago. Where hot material rises, plates pull apart, creating rifts where new crust forms. Where cool material sinks, plates converge, colliding or sliding beneath one another, destroying crust in a process called subduction. The theory that explains all this, plate tectonics, is surprisingly recent. It wasn't fully accepted until the Encyclopedia less than a lifetime ago. Before that, most scientists believed the continents were fixed in place, that the Earth's surface had always looked roughly as it does now. There were hints, of course, clues that something was wrong with that picture. As early as the 16th century, people noticed that the coastlines of Africa and South America seemed to fit together like puzzle pieces. In the early 1st century, a German meteorologist named Alfred Wegener proposed that the continents had once been joined and had since drifted apart. He called his idea continental drift, and he gathered evidence matching rock formations on opposite sides of the Atlantic, identical fossils of land animals on continents, now separated by thousands of kilometers of ocean, signs of ancient glaciation in places that are now tropical. But Wegener couldn't explain how the continents moved. He proposed that they plowed through the ocean crust, like ships through ice, but physicists calculated that the forces required would be impossibly large. Without a mechanism, continental drift remained a fringe theory, dismissed by most geologists. Now, it wasn't until the Encyclopedia and Lichters, when oceanographers began mapping the seafloor, that the evidence became undeniable. They discovered mid-ocean ridges, underwater mountain ranges where new crust was being formed. They found that the ocean floor was youngest at these ridges and progressively older, moving away from them. They discovered magnetic stripes in the seafloor rocks, recording reversals in Earth's magnetic field, symmetrical on either side of the ridges. The pattern was clear. The seafloor was spreading, pushing the continents apart. Suddenly, everything made sense. The continents weren't plowing through the ocean crust. They were being carried on tectonic plates, passive passengers on a journey driven by forces deep within the Earth. Continental drift wasn't just possible, it was inevitable, a fundamental feature of how our planet works. This understanding revolutionized geology and gave us the tools to reconstruct Earth's past geography. By studying the magnetism recorded in rocks, by mapping the ages of ocean crust, by tracking the distribution of fossils and rock types, scientists could run the plate movements backward, rewinding the drift of continents, seeing where they had been in the past. And when they did this, when they looked back far enough, they found Pangaea, not the first supercontinent. The Earth is old enough that the continents have gathered and dispersed multiple times, but the most recent one, and the one we understand best, Pangaea existed as a unified landmass from roughly 7 million years ago to about 8 million years ago. At its maximum extent, around million years ago, during the Permian and early Triassic periods, it contained virtually all of Earth's continental crust, a single enormous landmass surrounded by a single global ocean called Panthalassa. Imagine it, no Atlantic Ocean, no Indian Ocean. The Americas pressed against Africa and Europe, Antarctica nestled against Australia and India and Africa. All the continents we know, all the familiar shapes, locked together in an embrace that had taken hundreds of millions of years to form and would take hundreds of millions more to undo. The assembly of Pangaea was itself a story of collisions. The continents didn't simply drift together smoothly. They crashed together with immense force, crumpling their edges, thrusting up mountain ranges, creating the Appalachians in North America, the Atlas Mountains in Africa, the Ural Mountains that would one day mark the boundary between Europe and Asia. These weren't just any mountains, they were Himalayan scale ranges. Though erosion has since worn many of them down to worn stumps of their former height, the geography of Pangaea was strange and harsh. The supercontinent stretched from pole to pole, its vast bulk straddling the equator. The interior, far from any ocean, was a desert of extraordinary aridity. We have deserts today, the Sahara, the Gobi, the Australian outback, but they pale in comparison to the Pangaean interior. With no nearby ocean to provide moisture, with mountain ranges blocking what little humidity might have penetrated inland, the heart of Pangaea was as dry as any place Earth has ever known. Near the coasts, conditions were different. Monsoon systems, driven by the seasonal heating of the vast landmass, brought heavy rains to some coastal regions. But even these humid belts were unlike anything we see today. Because the monsoons could sweep uninterrupted across thousands of kilometers, creating weather patterns of a scale impossible on our fragmented modern Earth. Life adapted to these extremes. The Permian period, the time when Pangaea reached its full extent, saw the evolution of the first large herbivorous reptiles, synapsids that would eventually give rise to mammals. It saw the spread of early reptiles into every available niche. And it saw the Permian Triassic extinction, the Great Dying, the worst mass extinction in Earth's history, when over bifided chaucers of marine species and bifided pterosaurs of terrestrial vertebrate species vanished. The causes are still debated: massive volcanic eruptions in Siberia, sudden climate change, ocean anoxia, but the geography of Pangaea may have played a role, creating environmental conditions so extreme that life struggled to cope. In the Triassic period that followed, as life slowly recovered from the extinction, Pangaea began to show the first signs of the breakup to come. Rifts formed, long valleys where the crust was being stretched thin, where magma welled up from below. These rifts weren't yet oceans, just basins, sometimes filled with lakes, sometimes dry. But they were the beginning of the end. And over the next Ebot Chishurwur million years, these rifts would widen into seas, and seas into oceans, and Pangaea would tear itself apart, its fragments drifting to become the continents we know. The journey from one world to another, from Pangaea to today, is a story written in spreading seafloors and colliding margins, in extinct species and newly evolved ones, in rocks that remember magnetism and fossils that tell of ancient connections, now severed. It's a slow story measured in millions of years. But it's not over. The continents haven't stopped moving. The oceans are still growing and shrinking. And if we could fast forward through the next few 100 million years, we'd see the world transform again, the Atlantic eventually closing, the continents gathering once more into a new supercontinent, with a name we can only guess at, Pangaea Ultima, perhaps, or Amazia or Novo Pangaea. The Earth never stops, it never settles. And the map you grew up with, the shapes you learned in school, they're just a snapshot. A single frame in a film billions of years long, a film that will keep playing long after humans are gone, long after everything we've built has eroded into dust. Let's watch that film. Let's trace the breaking of Pangaea and see how the world we know came to be. The first crack appeared in the east, in what would become the Tethys Ocean. Even before Pangaea fully assembled, there was an embayment, a huge gulf between the northern landmass Laurasia and the southern one, Gondwana, a predecessor of the Mediterranean. But as Pangaea began to rift, this ancient ocean expanded, and new rifts opened elsewhere. The breakup didn't happen all at once. It was gradual, piecemeal, different parts of the supercontinent pulling apart at different times, driven by the same convective forces in the mantle that had brought them together. Hot mantle material rising beneath Pangaea created bulges in the crust, stretching it until it cracked. Magma filled these cracks, creating new crust. And as more magma intruded, the cracks widened into rifts, and rifts into seaways. The first major rift began around Arbeck million years ago in the early Jurassic period, splitting Pangaea into two large pieces, Laurasia in the north, containing what would become North America, Europe, and Asia, and Gondwana in the south, containing South America, Africa, Antarctica, Australia, India, and Arabia. Between them, the Tethys Ocean expanded, but even this wasn't a clean break. Laurasia and Gondwana remained connected in places, and both would undergo their own fragmentation in the tens of millions of years to come. The real story of Pangaea's breakup is one of multiple rifting events, each opening a new ocean basin, each sending fragments of the supercontinent on their own trajectories across the globe. The most famous of these rifts, the one that created the Atlantic Ocean, began around Ebite Basher's million years ago. If you could have stood on the eastern coast of North America at this time, you would have looked east and seen not ocean but land, the western coast of Africa and South America pressing close. The climate would have been hot, tropical, lush with vegetation. Dinosaurs would have roamed these coastal regions, moving freely between what we now think of as separate continents. Then the ground began to move, not suddenly, not catastrophically, but inexorably. A rift opened, running north-south, splitting the supercontinent. Magma welled up from the mantle, forming new oceanic crust. The rift widened year by year, centimeter by centimeter. Water from Panthalassa flooded into the growing gap. At first, it may have been a narrow seaway, perhaps even a series of salt lakes in a desert rift valley, under the tropical sun. But gradually, as the rift widened, it connected to the global ocean, and a new sea was born. This was the infant Atlantic Ocean, though it wouldn't be recognized as such for millions of years. Initially, it was narrow, perhaps resembling the Red Sea today, which is itself a young ocean in the early stages of formation, splitting Africa from Arabia. But the Atlantic continued to grow, fed by continuous seafloor spreading at the mid-Atlantic ridge, the underwater mountain range that still marks the boundary where new oceanic crust is formed. Okay. As the Atlantic widened, Africa and South America moved apart. North America separated from Europe and Africa. The continents that had been locked together for over Ebite million years were now independent, each on its own journey, each evolving its own unique flora and fauna. The timing of this split had profound implications for life. During the Jurassic and Cretaceous periods, as the Atlantic was opening, dinosaurs dominated the land. Early in the breakup, dinosaurs could still move between the separating continents via land bridges that persisted even as the ocean widened. This is why we find similar dinosaur fossils on both sides of the Atlantic from the early Jurassic. But as the ocean grew wider and the connections were finally severed, the dinosaur populations on each continent began to evolve independently, diverging into unique species found nowhere else. Meanwhile, other rifts were opening. Gondwana, the southern supercontinent, began its own fragmentation. Around Ebite Basher's million years ago, Madagascar and India began to separate from Africa, drifting eastward across what would become the Indian Ocean. India's journey would be particularly dramatic, a high-speed sprint in geological terms, racing northward across the Tethys Ocean toward Asia at rates of up to several centimeters per year for continental drift. Around Ebet sensors million years ago, South America and Africa began to separate from Antarctica and Australia. This opened the South Atlantic and began the isolation of the southern polar continent. Antarctica, which had been part of a larger landmass with a relatively temperate climate, was now on its own, drifting southward toward the pole, destined to freeze. Australia remained connected to Antarctica longer, not fully separating until about Sister Wu million years ago. When it finally broke free, Australia drifted northward, becoming the isolated island continent we know today. Its unique fauna, kangaroos, koalas, platypuses, evolving in splendid isolation, uncontested by the placental mammals that dominated other continents. Each of these rifting events created new ocean basins, new circulation patterns, new climate zones. The Atlantic, initially narrow and possibly quite salty due to high evaporation and limited connection to the global ocean, gradually grew into the vast ocean we know today. The Indian Ocean, formed by the rifting of India, Madagascar, and Africa from Antarctica and Australia, developed its own circulation, its monsoon winds, its unique ecosystem. The Pacific Ocean, which had existed as Panthalassa throughout the age of Pangaea, began to shrink. This might seem counterintuitive. If the Atlantic and Indian Oceans were growing, where did the space come from? But the Pacific was being consumed at its margins through subduction, oceanic crust diving beneath continental crust at places like the west coast of the Americas, creating the Ring of Fire, the belt of volcanoes and earthquakes that still encircles the Pacific today. This process, seafloor spreading creating new ocean crust at mid-ocean ridges, while subduction destroys old ocean crust at the edges, is how the Earth recycles its surface. Oceanic crust is young, geologically speaking. The oldest ocean floor is only about Arbeck million years old, formed during the breakup of Pangaea. Anything older has been subducted, consumed, melted back into the mantle. Continental crust, by contrast, can be billions of years old, too buoyant to be subducted, preserved through cycle after cycle of supercontinent formation and breakup. The rifting of Pangaea wasn't uniform or smooth. Some rifts succeeded, widening into oceans. Others failed, leaving behind fossilized scars called oolacogons, arms of failed rifts that didn't quite make it. The Mid-Continent Rift in North America, running through what is now Lake Superior, is one such failed rift formed during an earlier rifting event. If it had succeeded, North America might have split in two. Instead, it remains a geological curiosity, a scar of an alternate history that never came to be. By Ebet million years ago, in the middle of the Cretaceous period, the world was starting to look more familiar, though still quite different from today. The Atlantic was a substantial ocean, though narrower than it is now. South America and Africa were separated, but not yet as far apart as they are today. India was an island continent, midway on its journey toward Asia. Antarctica and Australia were still connected but beginning to rift. The continents we recognize were taking shape, but they were in different positions, under different climates, home to different life forms. The dinosaurs were at their peak during this time, but the world they inhabited was warmer than ours, with higher sea levels, shallow seas flooding large parts of the continents, creating epicontinental seaways like the Western Interior Seaway that split North America in two. There was no ice at the poles. Forests grew in Antarctica. Climate was globally warm, driven in part by high levels of volcanic activity associated with the ongoing breakup of Pangaea and the subduction of oceanic crust around the Pacific. Then, Locherlote million years ago, everything changed. An asteroid struck the Earth near what is now the Yucatan Peninsula in Mexico. The impact unleashed catastrophic environmental changes, Tsunamis, wildfires, a global dust cloud that blocked sunlight for months or years, a subsequent cold period followed by warming. The dinosaurs, except for birds, went extinct, along with about 3/4 of all species on Earth. The Cretaceous-Paleogene extinction reset the evolutionary playing field. Mammals, which had lived in the shadows of the dinosaurs for over million years, suddenly had opportunities. They diversified rapidly, spreading into niches left vacant by the dinosaurs' demise. And they did so on continents that were already largely separate, which meant that mammalian evolution took different paths on different continents. In South America, isolated from North America by a seaway, unique mammals evolved: giant ground sloths, massive armadillos, strange hoofed animals unlike anything alive today. In Africa, the ancestors of elephants, primates, and many modern mammal groups evolved. In Australia, still connected to Antarctica but otherwise isolated, marsupials dominated, evolving into the kangaroos, wombats, and other pouched mammals that still characterize the continent. But the continents weren't done moving, the rifting continued. The oceans kept spreading, and new collisions began. India's collision with Asia is one of the most dramatic events in the post-Pangaea world. Having drifted northward for over million years, India finally reached the southern margin of Asia around million years ago in the Eocene epoch. But it didn't stop. Continental crust can't be subducted, so when two continents collide, something else has to happen. The crust crumples, thickens, rises. The collision of India and Asia created the Himalayas, the tallest mountain range on Earth, and the Tibetan Plateau, the world's highest and largest plateau. This wasn't a quick event. The collision is still ongoing. The Himalayas are still rising, thrust upward by the continuing northward push of the Indian plate. Everest grows a few millimeters taller each year. The formation of the Himalayas changed the world's climate. The mountains blocked the flow of air from the north, creating the monsoon system that dominates South and Southeast Asian weather. The uplift and erosion of the mountains affected ocean chemistry, drawing down carbon dioxide from the atmosphere as weathered rock minerals reacted with company. Rainwater, potentially contributing to the global cooling that began in the Eocene and continued through the Oligocene and Miocene, eventually leading to the Ice Ages. And meanwhile, other continents were still moving toward their current positions. Around million years ago, the Arabian Peninsula, which had been part of Africa, rifted away, creating the Red Sea. It is still active. The Red Sea is widening, and in millions of years, it will become a full ocean, similar to the Atlantic. Around 10 million years ago, the Isthmus of Panama formed, connecting North and South America for the first time in about million years. This wasn't a rifting event, but the opposite: volcanic activity associated with the subduction of oceanic crust beneath Central America. Gradually built up an island arc that eventually formed a continuous land bridge. The formation of the Panama Land Bridge had enormous consequences. It allowed mammals to migrate between North and South America in an event called the Great American Interchange. North American mammals, predators like cats and dogs, herbivores like deer and horses, moved south. South American mammals, including armadillos, opossums, and porcupines, moved north. Many South American species couldn't compete with the invaders from the north and went extinct, though some, like opossums and armadillos, successfully colonized North America. The closure of the seaway between the Americas also changed ocean circulation. Water could no longer flow between the Atlantic and Pacific through Central America. Instead, warm Atlantic water began flowing northward along the east coast of North America as the Gulf Stream, carrying heat toward Europe, and contributing to the climate patterns we experience today. By arc million years ago, the world map looked very similar to what we see today. The continents were in roughly their current positions, though they continue to move. The oceans had their modern extents, though sea levels have fluctuated dramatically with the advance and retreat of ice sheets during the Pleistocene ice ages. And humans appeared, evolving in Africa, spreading across the Old World, eventually reaching Australia and the Americas. We emerged into a world shaped by the breakup of Pangaea, a world of separated continents, each with its own unique flora and fauna, a world of ocean basins and mountain ranges and climate zones, all created by the slow dance of tectonic plates. We've lived our entire existence on a moving platform, though we didn't know it until very recently. The ground beneath ancient Rome has moved meters since the city was founded. The ground beneath the pyramids has drifted since they were built. Mount Everest is taller now than when Hillary and Norgay first climbed it. The Atlantic Ocean is wider now than when Columbus crossed it. The Earth has never stopped moving, and it won't. The plates continue their slow journey, driven by heat from the Earth's core, by the cooling and sinking of oceanic crust, by forces we're still working to fully understand. So where is it all going? If we could fast forward through the next million years, what would we see? The continents don't stop at their current positions. They keep moving, and that movement will eventually change the map as dramatically as the breakup of Pangaea changed it. Geologists and geophysicists have created models based on current plate movements and our understanding of mantle dynamics, projecting the future geography of Earth. These aren't wild guesses, but extrapolations of measurable processes. Though, of course, there's uncertainty. Unexpected events, changes in mantle convection, new rifts could alter the trajectory. The most dramatic change already underway is the closing of the Mediterranean Sea. Africa is moving northward, pushing toward Europe at a rate of a few centimeters per year. Eventually, perhaps in Worcester's million years, the Mediterranean will close completely, and Africa will collide with Europe, creating a new mountain range that might rival the Himalayas. This collision will erase the Mediterranean, just as the collision of India and Asia erased the Tethys Ocean that once separated them. The Atlantic Ocean, which has been widening for Ebat Bashar's million years, will eventually reach its maximum extent and begin to close. New subduction zones may form along its margins, perhaps off the coasts of the Americas or Europe and Africa, and the ocean will start to be consumed. This process has already begun in the Caribbean, where the Atlantic oceanic crust is being subducted, creating the volcanic islands of the Lesser Antilles. The Pacific Ocean is already shrinking, consumed by subduction zones around its edges. This process will continue, and the Pacific may eventually close altogether, though that's hundreds of millions of years away. Australia is moving northward, sliding towards Southeast Asia at about 10 centimeters per year. In perhaps Worcester's million years, it will collide with Indonesia and mainland Asia, creating new mountain ranges and adding Australia to the Asian landmass. Antarctica remains at the South Pole for now, but its position isn't fixed. Over tens of millions of years, it too will drift, potentially moving northward into warmer waters, melting its ice sheets, transforming from frozen wasteland to habitable continent. And what of the Americas? North America is moving westward, pushing against the Pacific plate. Eventually, the Atlantic may close behind it, and North America might collide with Asia, closing the Arctic Ocean in the process. South America's trajectory is less certain, but it too is moving, and its eventual fate depends on how new subduction zones develop and where new rifts might open. Based on these projections, geologists have proposed several scenarios for the next supercontinent. One model, called Pangaea Ultima or Pangaea Proxima, suggests that the Atlantic will close and the Americas will collide with Africa and Europe, reforming something resembling Pangaea. All the continents gathered around what is now the Arctic, with a remnant Pacific Ocean on one side. Another model, Novo Pangaea, proposes that the Americas will remain separated from Africa and Europe by a narrow Atlantic, while Australia and Antarctica collide with Asia, creating a supercontinent centered on the current Pacific. And Morsher to Sti in Free Porgy in Men model to Crestish. A third model, Amasia, suggests that the continents will drift northward, converging on the North Pole, closing the Arctic Ocean and creating a polar supercontinent, with oceans remaining at the equator. At which scenario will actually play out, we can't be certain. The models depend on assumptions about how mantle convection will evolve, where new subduction zones will form, whether new rifts will open in unexpected places. But one thing is certain, a new supercontinent will form. The cycle of assembly and dispersal has repeated multiple times in Earth's history, and there's no reason to think it will stop now. Before Pangaea, there was Pannotia around Lobat million years ago. Before that, Rodinia around E billion years ago. Before that, Columbia around Eternbot billion years ago. Each supercontinent assembled, existed for a time, then broke apart, its fragments drifting and eventually reconvening in a new configuration. The cycle from breakup to reassembly takes about Subat Fu Wubak million years, the so-called supercontinent cycle, driven by the fundamental dynamics of plate tectonics. Why does this happen? Why do continents gather and then disperse repeatedly? The answer lies in the mantle. When continents gather into a supercontinent, they act like a thermal blanket, trapping heat beneath them. The mantle below a supercontinent heats up, becomes more buoyant, rises, and eventually bulges the overlying crust, creating rifts. The supercontinent breaks apart, and its fragments drift until they converge elsewhere, starting the cycle anew. It's a rhythm, a pulse, the heartbeat of the planet, operating on timescales that dwarf human civilization, but which are measured and understood through the patient work of geologists studying magnetic stripes on the ocean floor, matching rock formations across continents, analyzing the ages of ancient mountain belts, running computer simulations of mantle convection. And this cycle will continue for as long as Earth's interior remains hot, as long as there's enough heat to drive convection in the mantle, to move the plates, to recycle the. Eventually, billions of years from now, Earth's core will cool, the mantle will solidify, and plate tectonics will cease. The continents will freeze in place, the oceans will stop changing, and the dynamic planet we know will become static, geologically. But that's a fate so distant it's almost meaningless. For the next billion years at least, Earth will remain active. The plates will keep moving, and the map will keep changing. Long after humans are gone, the continents will continue their slow dance, gathering and scattering, opening oceans and closing them, building mountains and wearing them down. The Earth has a story, and it's not finished telling it. And the oceans themselves are not just passive gaps between continents. They're active, dynamic systems with their own stories, their own life cycles. An ocean is born when a continent rifts apart. It grows as seafloor spreading creates new crust. It matures, developing its own circulation patterns, its own ecosystems. And eventually it dies, consumed by subduction closing, as the continents on either side converge. The Atlantic Ocean is in its youth, still growing, still widening. The floor of the Atlantic is young, geologically speaking, the oldest parts dating only to the Jurassic, when the ocean first opened. The Mid-Atlantic Ridge, the underwater mountain range running down the center of the ocean, from Iceland to the Southern Ocean, is where new oceanic crust is born. Here, magma wells up from the mantle, cools and solidifies, adding a few centimeters of new crust each year. Okay? If you could drain the Atlantic and walk across its floor, you'd find a landscape as dramatic as any on the continents. The mid-Atlantic ridge rises thousands of meters above the surrounding abyssal plains, a mountain range that would rival the Rockies or Alps if it were above water. In places, it breaks the surface, forming islands, Iceland, the Azores, Ascension, Tristan da Cunha, isolated specks of land in the vast ocean, volcanic peaks marking the boundary between tectonic plates. The floor on either side of the ridge is not smooth, but scored with fracture zones, long east-west trending canyons where the ridge is offset by transform faults, places where the plates slide past each other horizontally rather than pulling apart. These fracture zones can extend for thousands of kilometers, cutting through the abyssal plains like scars. And everywhere there's life. The deep ocean, once thought to be lifeless, is now known to host vibrant ecosystems, especially at hydrothermal vents along the mid-ocean ridges. Here, superheated water, rich in minerals and chemicals, erupts from the seafloor, supporting communities of bizarre creatures. Tube worms meters long, giant clams, eyeless shrimp, all thriving in the darkness, using chemosynthesis rather than photosynthesis as the base of their food web. The Pacific Ocean, by contrast, is ancient and shrinking. Its floor, especially in the western Pacific, contains the oldest oceanic crust on Earth, dating back nearly Urbeck million years. The Pacific is surrounded by subduction zones, the ring of fire, where oceanic crust is consumed, diving beneath adjacent plates, melting and giving rise to chains of volcanoes. This is where earthquakes are most common, where tsunamis are generated, where the Earth's violence is most apparent. The Pacific is vast, covering nearly a third of Earth's surface, and it contains its own mid-ocean ridges, the East Pacific Rise being the fastest-spreading ridge system on Earth, creating new crust at rates up to stir-war centimeters per year. But despite this rapid spreading, the Pacific is shrinking overall because it's being consumed even faster at its margins. The Indian Ocean is intermediate in age and character, formed primarily by the rifting of India, Australia, and Antarctica from Africa, but also influenced by the complex tectonics of the region where the African, Indian, and Australian plates. The Indian Ocean has its own mid-ocean ridges, its own fracture zones, its own unique circulation driven by the monsoon winds, which reverse direction seasonally, creating ocean currents that change with the seasons, a feature unique among the world's oceans. The Southern Ocean, encircling Antarctica, is defined more by its circulation than its boundaries. The Antarctic Circumpolar Current, the world's largest ocean current, flows unimpeded around Antarctica, connecting the Atlantic, Indian, and Pacific Oceans, mixing their waters, playing a crucial role in global ocean circulation and climate. The Arctic Ocean, smallest and shallowest of the world's oceans, is nearly landlocked, connected to the Atlantic by narrow passages between Greenland, Iceland, and Norway, and to the Pacific by the narrow Bering Strait. It's covered by sea ice much of the year, though that ice is rapidly shrinking due to climate change. The Arctic is floored by some of the most complex oceanic crust on Earth, including the Gokul Ridge, the slowest spreading mid-ocean ridge, where volcanism and tectonics proceed at a glacial pace even by geological standards. Each ocean has its own character, its own history, its own fate, but they're all connected, part of a global system that has existed in some form for as long as there have been continents and water on Earth's surface. The first oceans formed over a billion years ago, when the planet cooled enough for water vapor to condense into liquid water. Since then, individual ocean basins have opened and closed many times, but the global ocean has persisted, covering most of the planet's surface. Each ocean has its own character, its own history, its own fate, but they're all connected, part of a global system that has existed in some form for as long as there have been continents and water on Earth's surface. The first oceans formed over billion years ago, when the planet cooled enough for water vapor to condense into liquid water. Since then, individual ocean basins have opened and closed many times, but the global ocean has persisted, covering most of the planet's surface, moderating its climate, enabling life, shaping the continents through erosion and deposition. The ocean is not separate from the story of continents. It's integral to it. The water that fills ocean basins doesn't just sit there passively. It circulates, driven by wind, by differences in temperature and salinity, by the rotation of the Earth itself. These circulation patterns, the great ocean currents that loop across thousands of kilometers, are highways for heat transport, carrying warmth from the tropics toward the poles, carrying cold water from the poles toward the equator, moderating global temperatures, making Earth far more habitable than it would be without them. The Gulf Stream, for instance, carries warm water from the Caribbean northward along the east coast of North America and then across the Atlantic toward Europe. This current is why Britain and Ireland, at the same latitude as Labrador, have such mild winters. It's why palm trees can grow in Cornwall, and why the harbors of Norway remain largely ice-free. Remove the Gulf Stream, and Northern Europe's climate would be transformed, becoming far harsher, more continental. But the Gulf Stream exists only because of the geography created by plate tectonics. The closure of the Isthmus of Panama, 10 million years ago, redirected Atlantic currents, strengthening the northward flow of warm water. If the Atlantic were shaped differently, if the continents were arranged differently, the current would be different or might not exist at all. The same is true for all major ocean currents. The Antarctic circumpolar current exists because Antarctica sits isolated at the South Pole, allowing water to flow unobstructed around it. Before Antarctica separated from South America, creating the Drake Passage, this current didn't exist, and global ocean circulation was fundamental. The opening of the Drake Passage about 6 million years ago allowed the Antarctic circumpolar current to develop, isolating Antarctica from contributing to the continent's glaciation and the onset of the modern Ice Age climate system. Every change in continental configuration changes ocean circulation, and changes in ocean circulation change climate. This is why the breakup of Pangaea wasn't just a story about moving land masses. It was a story about climate transformation, about the creation of new weather patterns, new monsoon systems, new ocean currents, all of which shaped the evolution of life. When the Panama Land Bridge formed and North and South American animals could finally intermingle, the result was dramatic. Most of the unique South American mammals went extinct, unable to compete with the invaders from the north. The terror birds vanished. The bizarre hoofed animals died out. The giant ground sloths eventually disappeared, though they persisted longer than most, some surviving until humans arrived in the Americas. Why did South American mammals fare so poorly in this exchange? The reasons are debated, but one factor may have been that North American mammals had been competing with each other and with Eurasian and African mammals during periods when land bridges allowed movement between the continents. They had been tested in a larger arena, honed by competition, and when they met the South American fauna, which had evolved in isolation, they often proved superior. This isn't to say South America contributed nothing to the exchange. opossums, armadillos, and porcupines successfully colonized North America and remain common today. But the traffic was primarily one way, a flood of northern species south that overwhelmed the endemic southern fauna. The story of this large island broke away from Africa around Ibad Bashar's million years ago and from India around Torser's million years ago, drifting in isolation in the Indian Ocean. The animals that happened to be on Madagascar when it separated, or that managed to reach it later by rafting across the ocean on floating vegetation, evolved into the unique fauna we see today. Madagascar has lemurs, primates found nowhere else, descendants of ancestors that rafted from Africa. It has fosses, cat-like carnivores that are actually more closely related to mongooses. It has tenrecs, small mammals that have diversified into forms resembling shrews, hedgehogs, moles, and even otters, though they're related to none of these. Madagascar is a natural experiment in evolution, showing what happens when a limited set of founding species is given an island and millions of years. And even continents that remained connected to others show the effects of geography on evolution. When India collided with Asia, the fauna of the two landmasses mixed but slowly, filtered by the rising Himalayas. Animals adapted to lowlands couldn't easily cross the mountains. Highland species remained isolated in the Himalayas and the Tibetan Plateau, evolving into unique forms like the yak, the snow leopard, the Himalayan tahr. The Mediterranean region, a crossroads between Europe, Asia, and Africa, has been repeatedly connected and isolated as sea levels changed, and tectonic movements opened and closed passages. This has created a mixing pot of species from 3 continents, a biodiversity hotspot shaped by the complex geological history of the region. When Pangaea existed, global climate was different. With only one large ocean, Panthalassa, and one large landmass, circulation patterns were simpler, but more extreme. The interior of Pangaea was cut off from ocean moisture, creating the vast desert. The coasts experienced massive monsoons, seasonal shifts of truly continental scale. There were no currents like the Gulf Stream because there was no Atlantic Ocean for them to flow through. As Pangaea broke apart, as the Atlantic and Indian Oceans opened, as the continents moved to their current positions, the climate diversified. Multiple ocean basins created multiple circulation patterns. The isolation of continents allowed different climate zones to develop. The formation of the Himalayas changed atmospheric circulation across Asia. The opening of ocean passages between continents altered the flow of currents. Each change cascaded through the system, creating the complex, varied climate we experience today. And life responded to all of this. Every climate shift, every new ocean current, every change in temperature or precipitation patterns selected for different traits, favored different species, opened new niches. The breakup of Pangaea wasn't just physical geography changing, it was the stage on which biological evolution performed, the backdrop against which the story of life on Earth unfolded. Okay, let's talk about what this means for life. The connection between plate tectonics and evolution is profound, though it took scientists a long time to fully appreciate it. And when Pangaea existed, life was relatively cosmopolitan. Land animals could migrate across the supercontinent. Species could spread from pole to pole if they could tolerate the climate zones in between. There was gene flow across vast distances. Populations remained connected. Okay? But as Pangaea broke apart, as oceans opened between the fragments, populations were separated. Gene flow was cut off. Isolated populations began to evolve independently, adapting to their local environments, responding to local selection pressures. Over millions of years, these isolated populations diverged, becoming different species, different genera, different families. Okay, this is why continents have unique flora and fauna. Australia's marsupials, South America's xenarthran sloths, anteaters, armadillos, Africa's Afrothers elephants, Hyraxes, tenrecs all evolved in isolation after the breakup of Gondwana. When these continents were connected, their ancestors were shared. But once separated, evolution took different paths. Australia was isolated, having separated from Antarctica and drifted northward into tropical waters. Australia became a laboratory for evolution unlike any other, with no placental mammals except bats, which could fly over the ocean, and later rodents, which arrived on floating vegetation or land bridges during periods of lower sea level. Marsupials diversified to fill every available niche. There were marsupial herbivores grazing the grasslands, marsupial carnivores hunting them, marsupial insectivores, marsupial equivalents of moles, marsupial gliders resembling flying squirrels, even a marsupial lion with retractable claws and bolt cutters for jaws. Evolution, given isolation and time, created a parallel universe of mammals as diverse in their own way as the placental mammals that dominated other continents, but built on a fundamentally different reproductive strategy. South America's isolation, from about Lixter's million years ago until the formation of the Panama Land Bridge, 10 million years ago, its own unique fauna. Here, placental mammals were present, descendants of animals that had lived on Gondwana before its breakup, but they evolved in isolation from the placentals of North America, Africa, and Eurasia. South America developed its own predators, like the terror birds, flightless avians that stood 3 meters tall and hunted with massive hooked beaks. It developed its own herbivores like Macrauchenia, a strange animal with a camel-like body and a trunk like an elephant. It had giant ground sloths the size of elephants, armadillos as big as cars, and bizarre hoofed animals called nota undulates that resembled combinations of rodents, horses, and rhinos, but were actually only distantly related to any of them. The Arctic, isolated at the pole by the northern landmasses, has its own unique fauna. Animals adapted to extreme cold and seasonal darkness, polar bears, Arctic foxes, caribou, muskoxen. These species evolved from temperate ancestors that adapted to the cooling climate. As the continents drifted into their current positions and the ice ages began, every ecosystem on Earth, every community of plants and animals, exists in its current form because of the geography created by plate tectonics. The tropical rainforests of the Amazon, the Congo, and Southeast Asia exist because those regions are near the equator and receive high rainfall, conditions determined by global circulation patterns, which are themselves shaped by the distribution of continents and oceans. The grasslands of the African savanna, the North American prairies, the Eurasian steppes, exist in rain shadows and temperate zones created by the positions of continents and mountain ranges. The coral reefs of the Indo-Pacific, the kelp forests of temperate coasts, the polar ecosystems of the Arctic and Antarctic all are where they are, supporting the species they support because of geography, and geography is written by tectonics. Even human evolution was shaped by these forces. Our ancestors evolved in Africa, but Africa's position and climate have changed dramatically over the past few million years. The rifting of East Africa, the formation of the East African Rift System, created the varied topography and climate zones where early homins evolved. The alternation between wet and dry periods, driven by orbital cycles but amplified by the geography of Africa, created selection pressures that favored adaptability, intelligence, tool use. When early humans left Africa, they encountered continents with different fauna, different climates, different challenges. The dispersal of humans across the world was fundamentally a journey across a geography created by the breakup of Pangaea. We walked from Africa to Asia across land bridges that existed at times of lower sea level. We rafted or walked to Australia when it was closer to Southeast Asia. We crossed from Asia to the Americas via Beringia, the land bridge that connected Siberia and Alaska during the ice ages when sea levels were low. Every human migration, every founding of a new population, every adaptation to local environment happened on a stage set by tectonics. And now, in the modern era, we spread across the entire world, inhabiting every continent except Antarctica, adapting to every climate zone, transforming the environment to suit ourselves. But we're still subject to the geography we inherited, still shaped by the distribution of land and water, still dependent on the climate systems created by ocean currents and atmospheric circulation. Patterns that exist because of where the continents happen to be right now. Right now, that phrase is important. Where the continents are right now is not where they were, and not where they will be. We live in a snapshot, a single moment in a long story, and that story continues. Let's return to the future, to where this is all going. We talked earlier about the models for the next supercontinent, Pangaea Ultima or Amasya or Novo Pangaea. These models differ in details, but they agree on the fundamentals. The continents will gather again. It's inevitable as it was that Pangaea would break apart. Okay, but let's think about what it means for a supercontinent to form again. It's not just the continents moving, it's oceans closing. It's species going extinct as their habitats disappear or merge. It's climates changing as circulation patterns shift. It's mountain ranges rising as continents collide. It's the entire surface of the planet transforming. Imagine the closing of the Atlantic Ocean. Right now, the Atlantic is about 11 kilometers wide at its maximum. It grows about 8 centimeters wider each year. If that process reversed, if subduction zones formed along the Atlantic margins and the ocean began to close, it would take about 6 million years for the Atlantic to vanish completely, for the Americas to collide with Europe and Africa. During those 6 million years, what would happen? The mid-Atlantic ridge would become a trench as it was subducted. Iceland would vanish, consumed by the closing ocean. The Azores, Bermuda, Ascension Island, all would disappear. The ocean floor, all the young basaltic crust created over the past million years, would be recycled. Marine species that evolved in the Atlantic would either adapt to the shrinking ocean, migrate to other oceans, or go extinct. Coastlines would change as the continents approached. Cities on the Atlantic coasts, if humans still existed and built cities in the same places, unlikely over such time scales, but bear with me, would find the ocean receding, the coast moving away as the ocean narrowed. Eventually, the continents would collide. North America would crunch into Europe. South America would slam into Africa. The impact would be slow by human standards, centimeters per year, but inexorable. The collision would crumple the continental margins, thrusting up new mountains. These wouldn't be like the worn-down Appalachians of today. They'd be fresh, young, Himalayan scale peaks, the Appalachians reborn, rising from the same rocks that formed the original range when North America and Africa collided to form Pangaea. And this would just be one part of the new supercontinent's formation. Australia would collide with Asia, adding more mountain ranges. Antarctica might drift northward, melting its ice and contributing its landmass to the gathering. Africa's northward journey would close the Mediterranean, creating another mountain range where that sea once was. And the new supercontinent, whatever we call it, would have a different geography from Pangaea. The continents would be arranged differently. The interior might be desert again, or it might have lakes, vestiges of the oceans that closed. like the Caspian Sea today, is a remnant of an ancient ocean called Paratethys. The coastline would face a shrunken Pacific or a new ocean formed by rifting of one of the continents before it could reach the others. And what of life during this transformation? Evolution doesn't stop. As the continents approach each other, land bridges form, allowing animals to migrate between land masses that had been separated. Species from different evolutionary lineages would meet, compete, interbreed if closely enough related, or divide up the available niches if different enough. We've seen this before. The Great American Interchange, 10 million years ago, was a preview of what happens when long-separated landmasses reconnect. The mixing of Asian and American fauna when humans first crossed Beringia was another example. But the formation of a supercontinent would be this process on a global scale, every continent's fauna meeting, mixing, competing, evolving. Some lineages would win, others would lose. The ecosystems that had existed on separate continents would break down and reform in new configurations. And then after some tens of millions of years of this continental scale mixing, the supercontinent would start to rift apart again, and the process would reverse, populations separating, evolving in isolation, diversifying once more. Now, this is the pulse, the rhythm we mentioned earlier. The supercontinent cycle is not just a physical phenomenon. It's a biological one. Evolution is driven by isolation and mixing, by populations separating and later reuniting. Continent cycle provides both, alternating between periods when continents are gathered promoting mixing and competition, and periods when they're dispersed promoting isolation and diversification. Some scientists think this cycle has been crucial for the evolution of complex life on Earth. The alternation between supercontinent and dispersed continents creates environmental diversity, climate extremes, ecological opportunities. It drives evolution, maintains biodiversity, prevents stagnation. Other planets might not have this. Venus has no plate tectonics. Mars may have had it early in its history, but doesn't now. Earth might be unique in our solar system in having a surface that recycles itself, that transforms itself, that provides this endless churning that drives evolution. This is worth pausing on. The continents moving, the oceans opening and closing. These aren't just interesting geological facts. They might be essential for life as we know it. They might be the reason Earth has such rich biodiversity, such complex ecosystems, such a long history of evolutionary innovation. And without plate tectonics, Earth might be a dead world, or if not dead, then static, unchanging, with life that evolved once and then stayed the same, unable to diversify without the isolation provided by moving continents, unable to innovate without the environmental changes driven by shifting geography. This is speculative, of course. We have only one Earth to study. But it's a provocative idea that the very restlessness of our planet, the fact that it never settles, never finds equilibrium, is what has made it so alive. Let's bring this back to human timescales, because our bagnillion years is hard to grasp. We live maybe Batashor years if we're lucky. Civilizations last a few thousand years. Recorded history goes back, maybe Wuling years. The entire existence of Homo sapiens as a species is only about Sambaitling years. Against the time scales we've been discussing, human existence is nothing, a blink, less than a blink. If Earth's history were compressed into a single year, humans would appear in the last few minutes before midnight on December Sensory Saint. All of recorded history would be the last few seconds, but in another sense, we're extraordinarily privileged. We exist at a time when the continents are dispersed, when the oceans are full, when the world map is complex and varied. We exist in the middle of an ice age, paradoxically, though we call our current phase an interglacial because the ice sheets have temporarily retreated. We exist at a time when the Himalayas are high, when the Amazon rainforest flourishes, when coral reefs ring tropical islands, when the biodiversity of Earth is, despite our impacts, still immense. A few million years earlier, and we would have seen the Isthmus of Panama still forming, the final connection of North and South America still incomplete. A few million years later, and we might see the Mediterranean beginning to close, Africa grinding toward Europe. A few tens of millions of years earlier, and we'd see a world with no ice at the poles, with warm forests in Antarctica. A few tens of millions of years later, and we might see the Atlantic beginning to close, the next supercontinent starting to form. And we happen to live now in this particular configuration of continents and oceans, this particular state of the global climate system. It's the world we evolved in, the world we're adapted to, the only world we've ever known. But it's not the only world Earth has been or will be. This should give us perspective. The geography we take for granted, the borders between oceans, the shapes of continents, the heights of mountains, all of this is temporary. Not temporary in human terms, these features will outlast our civilization, our species, possibly even our genus. But temporary in geological terms, fleeting in the context of Earth's Sudentwuv billion-year history. The Atlantic Ocean, that vast body of water that defined human history, that separated the old world from the new, that posed such a barrier to exploration and trade, that ocean is a youngster, barely, Ebite Basher's million years old. It didn't exist when dinosaurs first evolved. The Tethys Ocean, which no longer exists, was far older. The Pacific is older still, though even it is not primordial. It's a descendant of Panthalassa, but not the same ocean, just as the current Atlantic is not the same as ancient oceans that once separated the continents before Pangaea formed. Mountains, too, are temporary. The Himalayas, the Alps, the Rockies, these are young mountain ranges, sharp and high, because they haven't yet been worn down by erosion. Give them about million years, and they'll be rounded hills, worn stumps like the Appalachians or the Urals. Give them Arbeck million years, and they might be nearly gone, planed flat by the patient work of water and wind and ice. But new mountains will rise. The cycle continues. As long as the plates move, there will be collisions, and collisions build mountains. The mountains we see today will erode, but others will take their place in other locations, thrust up by new continental collisions we can only guess at. Again, even the existence of continents at all is not guaranteed forever. Earth has had continents for most of its history, but the balance between creation of continental crust and destruction of it could shift. If subduction became more efficient at recycling continental crust, the continents could shrink, eventually disappearing entirely, leaving a water world with only oceanic crust. This seems unlikely. Continental crust is buoyant and resists subduction, but it's not impossible over billion-year timescales, where the continents could grow. Some models suggest that Earth's continental crust has been steadily growing throughout the planet's history, that there's more of it now than there was a billion years ago, and there will be more in the future. If this continues, the continents could eventually cover more of Earth's surface, shrinking the oceans. The future is uncertain. We can project based on current movements, but we can't predict unexpected changes, new rifts opening where we don't expect them, changes in mantle convection patterns altering plate movements, major asteroid impacts. Earth has surprised us before, and it will again. But in another sense, we're extraordinarily privileged. We exist at a time when the continents are dispersed, when the oceans are full, when the world map is complex and varied. We exist in the middle of an ice age. Paradoxically, though we call our current phase an interglacial because the ice sheets have temporarily retreated. We exist at a time when the Himalayas are high, when the Amazon rainforest flourishes, when coral reefs ring tropical islands, when the biodiversity of Earth is, despite our impacts, still immense. A few million years earlier, and we would have seen the Isthmus of Panama still forming, the final connection of North and South America still incomplete. A few million years later, and we might see the Mediterranean beginning to close, Africa grinding toward Europe. A few tens of millions of years earlier, and we'd see a world with no ice at the poles, with warm forests in Antarctica. A few tens of millions of years later, and we might see the Atlantic beginning to close, the next supercontinent starting to form. And we happen to live now in this particular configuration of continents and oceans, this particular state of the global climate system. It's the world we evolved in, the world we're adapted to, the only world we've ever known. But it's not the only world Earth has been or will be. This should give us perspective. The geography we take for granted, the borders between oceans, the shapes of continents, the heights of mountains, all of this is temporary. Not temporary in human terms, these features will outlast our civilization, our species, possibly even our genus. But temporary in geological terms, fleeting in the context of Earth's Sudentwuv billion-year history. The Atlantic Ocean, that vast body of water that defined human history, that separated the old world from the new, that posed such a barrier to exploration and trade, that ocean is a youngster, barely, Ebite Basher's million years old. It didn't exist when dinosaurs first evolved. The Tethys Ocean, which no longer exists, was far older. The Pacific is older still, though even it is not primordial. It's a descendant of Panthalassa, but not the same ocean, just as the current Atlantic is not the same as ancient oceans that once separated the continents before Pangaea formed. Mountains, too, are temporary. The Himalayas, the Alps, the Rockies, these are young mountain ranges, sharp and high, because they haven't yet been worn down by erosion. Give them Ebite million years, and they'll be rounded hills, worn stumps like the Appalachians or the Urals. Give them Arbeck million years, and they might be nearly gone, planed flat by the patient work of water and wind and ice. But new mountains will rise. The cycle continues. As long as the plates move, there will be collisions, and collisions build mountains. The mountains we see today will erode, but others will take their place in other locations, thrust up by new continental collisions we can only guess at. Again, even the existence of continents at all is not guaranteed forever. Earth has had continents for most of its history, but the balance between creation of continental crust and destruction of it could shift. If subduction became more efficient at recycling continental crust, the continents could shrink, eventually disappearing entirely, leaving a water world with only oceanic crust. This seems unlikely. Continental crust is buoyant and resists subduction, but it's not impossible over billion-year timescales, where the continents could grow. Some models suggest that Earth's continental crust has been steadily growing throughout the planet's history, that there's more of it now than there was a billion years ago, and there will be more in the future. If this continues, the continents could eventually cover more of Earth's surface, shrinking the oceans. The future is uncertain. We can project based on current movements, but we can't predict unexpected changes, new rifts opening where we don't expect them, changes in mantle convection patterns altering plate movements, major asteroid impacts. Earth has surprised us before, and it will again, but let's return to the present one more time and think about what it means to live on a moving planet. You're sitting somewhere right now, reading or listening to this. You feel still. The ground beneath you feels solid, permanent, but you're not still. You're moving in multiple ways simultaneously. You're moving because Earth is rotating, spinning on its axis, carrying you eastward at speeds that vary with latitude, but that can reach over loop at kilometers per hour at the equator. You're moving because Earth is orbiting the Sun at about ibetling chi ling kilometers per hour. You're moving because the Sun is orbiting the center of the galaxy at about batbaidar serba ling kilometers per hour. You're moving because the galaxy itself is moving through intergalactic space. But you're also moving because the ground beneath you is moving. The tectonic plate you're on is drifting. If you're in North America, you're moving away from Europe at about 1 centimeters per year. If you're in Australia, you're moving northward toward Asia at about chi centimeters per year. If you're in the Mediterranean region, you're caught in a complex zone where Africa is pushing into Europe, and the local motion might be different depending on exactly where you are. This motion is too slow to feel. You'll never feel it. No human has ever felt the motion of tectonic plates. It's far too slow, too smooth. But it's real and it's measurable. Using GPS, using measurements from satellites, we can detect this motion, track it, predict where the plates will be in the future. And this motion has consequences. Earthquakes happen because of it. When stress built up by plate motion is suddenly released. Volcanoes erupt because of it, where subduction melts crust or rifting allows magma to rise. Mountain ranges rise because of it, where plates collide. Ocean basins open because of it, where plates pull apart. Every landscape feature on Earth, every geological phenomenon, traces back ultimately to plate tectonics, to the motion of the ground beneath our feet. And this motion never stops. Even as you read this, the plates are moving. New oceanic crust is forming at mid-ocean ridges. Old oceanic crust is being subducted at trenches. Continents are drifting. Mountains are rising. The map is changing. The change is imperceptible in a human lifetime. It's barely noticeable even over the span of human civilization. The continents are in almost exactly the same positions they were when the first cities were founded, when agriculture began, when humans first spread out of Africa. The total motion has been measured in meters, maybe tens of meters in a few cases. Not enough to change the map in any meaningful way, but over geological time, this imperceptible motion accumulates. The centimeters become kilometers, the kilometers become continents rearranged, and the world transforms. And this is the challenge of understanding deep time, of grasping what geology teaches us. The timescales are so far beyond human experience that they're almost incomprehensible. We can say, ebet million years, we can write the number, we can calculate what it means for plate movements, but can we truly grasp it? Can we feel in our bones what it means for time to stretch that far? It's like trying to understand the size of the galaxy or the age of the universe. The numbers are available, the math is simple, but the reality is beyond our intuition. We're creatures adapted to human timescales, human distances. We understand years and decades. We can sort of grasp centuries if we think about history. Millennia stretch our comprehension. But millions of years? Hundreds of millions? Billions? And yet this is the story of our planet. This is where we live, on a restless Earth that has been changing for billions of years and will continue changing for billions more. We're embedded in this story, a brief chapter in a very long book, but we're here nonetheless, able to read the earlier chapters in the rocks, able to project the later chapters through models and mathematics, has a sobering effect. It forces us to reconsider our worries, our disputes, and even our civilizations from a wider viewpoint. What we often assume to be permanent, national borders, cultural identities, political structures, last only a few centuries, perhaps a couple of thousand years at most, before disappearing and giving way to something new. The land beneath the Roman Forum has shifted by meters since Rome was first established. The ground beneath the Great Pyramid has slowly drifted since its construction. Even these structures we label as timeless have been carried across the surface of a planet that knows nothing of permanence, constant. Yet this realization is also deeply motivating. We are participants in this grand narrative. We are shaped by this planet, having evolved within environments formed by drifting continents and adapted to climates influenced by ocean currents determined by the arrangement of land. Our very presence is the result of plate tectonics, of populations separating and reconnecting, of the ecological variety created by moving continents. And as far as we can tell, we are the first species capable of understanding this process. We are the first to observe the world not only as it is, but as it once was and as it may become. We are the first to decipher the history preserved in stone, to reconstruct Pangaea, and to imagine the formation of future supercontinents. We are the first to grasp the concept of deep time, and to place ourselves within a timeline spanning billions of years. This is an astonishing accomplishment. Over the Earth's Sudan-Wove billion-year history, among the countless species that have existed and vanished, only in the last few decades has a species emerged with the ability to comprehend the planet's past, to recognize the larger picture, and to appreciate the vast scale of geological time. And this understanding should never be taken lightly. Knowledge of this kind is rare and invaluable. The rocks have always existed, waiting to be interpreted. The continents have always been in motion. Mountains have continually risen and worn away. Yet for most of Earth's existence, there was no observer, no mind capable of seeing, understanding, or valuing the immense story unfolding over billions of years. Now, we exist in a fleeting moment where we can look backward into the deep past and forward into the distant future. We can envision Pangaea, watch it fragment, and imagine the next supercontinent yet to form. We can situate ourselves within deep time and understand, at least intellectually, our place in the long narrative of this planet. Bonda. So what should we do with this awareness? How ought it to influence the way we view the world and conduct our lives? I don't claim to have definitive answers. These questions are personal, philosophical, perhaps even spiritual. But a few reflections can be offered. First, this perspective teaches humility. We are not the center of the universe, nor even the central focus of Earth's story. We are a recent arrival, a brief episode, possibly a minor one in the grand scheme. The planet thrived for billions of years before we appeared and will continue for billions more after we're gone. Continents will continue to drift, oceans will continue to change. The story will move forward, whether we are part of it or not. This can be uncomfortable. We like to think we matter, that our actions have meaning, that we're important. And in human terms, we do matter. Our actions do have meaning. We are important to each other and to the other species we share this planet with. But in geological terms, we're insignificant. We're a thin layer in the rock record, a brief spike in carbon dioxide concentrations, a momentary rearrangement of the surface. We'll leave traces, certainly. Future geologists, if there are any, will be able to identify our age by plastics in the sediment, by radioactive isotopes from nuclear testing, by the extinction of species we caused. But we won't change the fundamental trajectory of the planet. The plates will keep moving. The supercontinent cycle will continue. Second, it gives us perspective on our impacts. We worry, rightly, about climate change, about biodiversity loss, about our transformation of the planet. And we should worry. These are real problems with real consequences for us and for the countless species we share this planet with. But in geological context, what we're doing is not unprecedented. Earth has been warmer before. It's been colder before. Carbon dioxide levels have been higher and lower. Species have gone extinct in mass extinctions far more severe than anything we've caused yet. The planet has survived asteroid impacts, supervolcanic eruptions, periods when the oceans were anoxic and hostile to most life. And this doesn't mean our impacts don't matter. They matter immensely to us and to current ecosystems. But it means the planet will survive us. Life will survive us. In 1,000,000 years, in 10 million years, the ecosystems we've disrupted will have recovered or been replaced by new ones. The species we've driven extinct will be replaced by new species evolved to fill their niches. The elevated carbon dioxide will have been drawn down by weathering and by the patient work of life. The planet will have moved on, barely noticing that we were here. This is not an excuse for inaction. It's not a reason to stop caring about conservation or climate change. It's just context. We need to act to preserve the world we know, the ecosystems that exist now, the species that exist now, because they matter to us and in their own right. But we should also recognize that from the planet's perspective, from the perspective of deep time, this is just another chapter, another event in a long story that has included many events, many extinctions, many transformations. Third, and perhaps most importantly, understanding deep time should give us wonder. The story of Pangaea, the story of continents drifting and oceans opening and mountains rising, is not just a science. It's a story of transformation, of change, of a planet that is alive in a sense, that is dynamic and active and constantly creating itself anew. We live on a planet that has never been still. That's remarkable. That's beautiful. And that's something worth appreciating, worth celebrating, worth sharing with others. The rocks beneath your feet are travelers. They've been on journeys you can barely imagine. They've crossed oceans, been thrust up into mountains, been worn down by erosion, been subducted into the mantle and melted and risen again as new mountains. They've been to the equator and the poles. They've been underwater and kilometers above sea level. They've witnessed the evolution of life, the extinction of species, the transformation of ecosystems, and they're still traveling. The journey isn't over. The plate they're part of is moving right now, carrying them towards some future collision or rift, some destiny that won't be fulfilled for tens or hundreds of millions of years. You are standing on a piece of a planet that is in motion, that is changing, that is part of a story billions of years long. That should fill you with awe. Okay? As we reach the end of this journey through deep time, let's come full circle. We started Sambite Sensor Wu million years ago, watching the continents gather into Pangaea. We watched Pangaea break apart, splitting into Laurasia and Gondwana, then fragmenting further into the continents we know. We saw the Atlantic Ocean born, narrow seaway, growing into vast ocean. We saw India race across the Tethys and collide with Asia, thrusting up the Himalayas. We saw Australia drift northward, Antarctica freeze, the Americas separate and then reconnect at Panama. Okay? We traced the journey from one world to another, from a world of one supercontinent and one superocean to a world of 7 continents and 5 oceans, from Pangaea to today. Okay, but today is not the end. It's just another moment in the story, no more permanent than any other. The continents are still moving. The oceans are still changing. The mountains are still rising and eroding. And in the future, perhaps Urbector, Sambite million years from now, the continents will gather again, the oceans will close, and a new supercontinent will form. That supercontinent will be as different from today's world as today's world is from Pangaea. It will have different geography, different climates, different life forms. If any species survive that long, they will be so changed from their ancestors today as to be unrecognizable. Evolution never stops, and Urbeg million years is enough time for profound change. And then that supercontinent, too, will break apart. New oceans will open, new continents will drift. The cycle will continue, as it has for billions of years, as it will for billions more, until the Earth's interior cools and the engine that drives plate tectonics finally stops. But that's so far in the future as to be almost beyond imagination. For now, for the foreseeable future, the Earth remains active, dynamic, alive. The maps are moving. The oceans are breathing. And the ground beneath us, solid as it seems, is adrift on a planet that has never known stillness. I hope this journey has changed how you see the world. I hope that when you look at a map now, you don't just see borders and countries but continents in motion. I hope when you see mountains, you think about the collisions that created them and the erosion that's wearing them down. I hope when you see the ocean, you think about the mid-ocean ridges where new crust is being born and the subduction zones where old crust is dying. The world is not static. It never has been. It never will be. And that's not something to lament, but to celebrate. We live on a planet that is endlessly creative, endlessly transforming, endlessly writing new chapters in a story that stretches back to the formation of the Earth itself and forward into a future we can only glimpse. From Pangaea to today, from today to the next supercontinent, from the birth of the Earth to its distant end, billions of years from now when the sun expands and the oceans boil away and the planet becomes a lifeless rock. This is the story, the long story, the story written in stone and time, the story of a restless planet that we are privileged to live on, to study, to understand, if only for a brief moment before we too pass, and the story continues without us. Thank you for joining me on this journey through deep time. If this quiet exploration of Earth's grand story resonated with you, I'd be grateful if you tapped like or subscribed. And wherever you are right now, whatever ground you're standing on, take a moment to appreciate that it's been on a journey, that it's still traveling, that you're standing on a piece of a planet in motion, a ship adrift on the slow currents of geological time. The Earth never stops, the story never ends, and that perhaps is the most wondrous thing of all. And until next time, this is Nick's Documentaries, signing off from a planet that is always changing